Sorry about that. So the oscillating discontinuity, like I said, it continues to oscillate so much that it gets caught and can't get past. Now, usually, you've got like the opposite thing happening, and then like on the other side, it'll do this same type of thing where it'll keep oscillating, and then it'll get caught, and then there's this like big mass of oscillation in the middle. So it kind of looks something like that by the time you're done. Now, like I said, those are really, really rare. But the idea is that it oscillates so much that it can't continue on, so it's discontinuous there. So those are the big four, but three of them are much more common. Okay, sorry. So these are the points of discontinuity, or different types. So if I give you a function, I might ask you then to identify where in the function is there a point of discontinuity. And so usually we need to know a little something about the graph of the function or how it's put together, that sort of thing, to be able to identify some of those. So let's try that a little bit. We'll take a look at some functions and see if we can identify where these things might come about. So, all right. So how about f of x equals 1 over x minus 2? This particular function has a point of discontinuity. So of the four that we talked about and what you know about these types of functions here, what kind of discontinuity do you suppose this one has? Infinite, right. Because we know 1 over x minus 2 has a vertical asymptote in it, okay? And that's an infinite discontinuity. All right, so the graph of this thing looks something like this. So we would say for this particular function, there's an infinite discontinuity at x equals 2. So 2 is where we're having the problem. Okay, that's where we can't, keep going with the function without picking up our pencil. It doesn't fit the definition. The limit to the left and the right are not equaling the value of the function because there is no value of the function there. Doesn't work. Another one. Let's do, and this one, there's going to be some of these where you're not going to be able to really see it unless you do it on your calculator. So this one I'm going to make a calculator-friendly question here. But what if we had absolute value of x divided by x? Take a minute on your calculator and graph that thing and take a look at it and see if you can identify what kind of discontinuity is going on for that one. Because I'm guessing you guys probably don't know what this one looks like offhand. All right, so if graphed correctly, it should look like this. Now, your calculator is not going to put the big open circles there, but we know they have to be open circles because this thing is undefined for x equals 0. Okay? But correct. Yeah, it can't include 0 at all, so neither piece has the 0 included there. But your graph on your calculator should have looked like two lines coming to the axis and stopping, right? When you did this one. So what type of discontinuity are we looking at for this one then? That's definitely a jump. Yep. So we got a jump discontinuity at x equals 0 for that one. Okay, so this is going to be kind of, with these, it's going to be kind of a mix of ones that you know what they look like, that are non-calculator ones, okay, like the first one. Other ones that are a little bit more out there that you haven't seen that you can use your calculator for. But still, just being able to identify what type of point of discontinuity do you have going on, okay? So, that being said, now we get into this whole thing of, okay, we know continuity at a point. What does it mean to be a continuous function then? People often confuse the two, or they assume they're the same thing, and they're not exactly the same thing. So a continuous function, the definition of this reads as follows. It is a function that is continuous at every point on its domain. And the key phrase for this is on its domain. Okay, because if there are points that are not in the domain, you could have points of discontinuity yet have a continuous function. If the point of discontinuity is simply not in the domain, then it could still be a continuous function. I'll give you an example of that. We'll go back to our reciprocal friend here. Let's just do 1 over x. What's the domain for 1 over x? Everything except for 0, right? Okay, so this would be a continuous function if it's continuous on this interval and continuous on this interval. Okay, so let's draw a quick sketch of what this thing looks like. So look at the function. Is it continuous on the interval negative infinity to 0? Yes, it is, right? That's this little piece down here. And this is, there's nothing getting in the way of this little piece here. From negative infinity to 0, not including 0. So we don't have to worry about the fact that it never actually gets to 0. But this entire piece right here is continuous. Okay. Is it continuous on 0 to infinity? Yup, same thing. Over here, nice and smooth, continuous, nothing getting in the way over there. So, believe it or not, 1 over x is a continuous function. It fits the definition.
So would most functions that have infinite discontinuity be a continuous function?
Yes. Yep, infinite discontinuities. Oops, that should be is a continuous function. Infinite discontinuities, because they by nature take a number out of the domain, don't really affect if a function is considered a continuous function or not. Yep. The only ones you really need to be focusing on for this idea is, do we have any removables or do we have any jumps? Those are where we're going to have issue. Yeah, question? Oh, that means therefore. Sorry. Yeah, so therefore, 1 over x is a continuous function. Good question. I don't think I've shown you that before. Okay, so about an example of a function that isn't continuous then. Well, we talked about it before. The step function. And it looks something kind of like this. Okay, so and then etc., that way, and etc., that way. So what is the domain of that particular function? Everything, right? There are no x values not accounted for there. So, for this one then, same question. Is it continuous at every point on the domain? No, right? The domain is everything, but there are points of discontinuity at every integer as you go along on this thing. Okay? So, we have jump discontinuities at each integer which are in the domain. So, therefore, int x is, should say is not a continuous function. Okay, so part of your work, what you're going to be doing is identifying what's continuous or what's a continuous function and what's not. So you got to focus on the domain. Okay, is that continuity at a point thing happening at every single point that's in the domain or not? Okay, and so those are some examples of the two ways that can go. All right.